Welcome back. And let's solve another optimization problem. So in the last video, we saw that we wanted to create a rectangular region, and on three sides of the rectangle we wanted to use wire fencing, and one side we needed to use wooded fencing. And these are the prices per linear foot. The um, the um, and in the previous video we were given $320, and we wanted to see what is the maximum possible area that we can enclose within the rectangle with the $320 constraint. Now in this video we're kind of going to do this opposite. That is, now we are given that we are still trying to create a rectangular region with wired fencing on three sides and wooded fencing on one side, with the same prices for the wire fencing and the wooded fencing. But this time we are told that the enclosed area must be 810. The area of the enclosed region must be 810 square feet, and so then we need to minimize the cost. So that is, what is the minimum cost of building this fence, and what are the dimensions of this rectangle. So now we have fixed area that we want to enclose, and we just want to minimize the cost of fencing. Well, we already know the cost function from the previous video. The cost function would be 8x plus 2x, so that's 10x, and then 2l plus 2l, so that's 4l. This is the cost function. That's what we want to minimize, and we are given that the area is XL, and that has to be 810. Now from this equation we can solve for L, and L is 810 divided by X. And so notice that clearly X has to be positive because we are talking about a length here, and notice that X could be any positive number. So I can pick X as big or small positive number as I choose. So if I pick X too big, then I have to pick L very small. If I pick X too small, then I have to pick L very big to make sure that X times L is 810. But we can take X to be whatever positive value we want, and then we will pick L by this, we'll pick L equal to this fraction, and then this requirement will still be satisfied. So X could be anything. So basically then we want to minimize the cost function subject to the constraint that L is 810 X inverse. And we can plug in the value of L in the cost function, so we get 10x plus 4 times 810 times x to the negative 1, which we can write as 4 times 810 is 3,240. So this is the function that we need to minimize, and so to find the minimum value we take the derivative. So the derivative would be 10 minus 3,240 times x to the negative 2, which is the same as 10 minus 3,240 divided by x squared, and we can add this to and write it as 10x squared minus 3240 over x squared. Now we see that we see that in the numerator, by looking at the numerator, we know that the derivative is 0 when when this numerator is 0, and this numerator is 0 when x squared is 3240 divided by 10, which is equal to 324, or when x is the root of 324, so that's plus or minus 18. But minus 18 is not in the, remember x couldn't be negative, so we can discard negative 18 and just keep 18. So that's the only critical point. And by using the second derivative test, what's the second derivative? Well, it's the derivative of the first. So recall that this is the first derivative, and if I take the derivative again, we get negative 3240 multiplied by negative 2, so that's going to be 6480 times x to the negative 3. And what's the value? So that's 6480 over x cubed. What's the value of the second derivative at 18? Well, whatever it is, it's positive, so we know that the cost function is concave up at this critical point 18. So it has the local minimum at 18, and that's going to be the absolute minimum as well. So so we see that the cost is minimized for x is 18. When x is 18, we can use the formula for L, and we see that L is 810 divided by 18, which is 45, and then the length should be 45, and the width should be 18 feet, and then the minimum cost would be $360. So to build a rectangular area with fencing with fixed area 810, the minimum cost that will be required is $360. All right, this is it in this video, and I'll see you in the next video.